All right, today we're starting chapter 6, in which we're going to be talking about polygons. And we've talked a bit about these already this year, and a lot of it was review even from previous years. So to start the chapter, we're going to look at some of this review information about just the basics of what polygons are and remembering some of the vocabulary. So poly means multiple, so more than one. Mono means one, poly means multiple. Gon technically means angles, so this is a multiple angled figure, but we also think of it as a multiple sided figure. It's sometimes easier to think of a shape in terms of the sides because that's how we draw it. The angles are kind of like a byproduct of drawing those sides. So we draw lines or line segments, and where they intersect, angles are formed. So yes, it is a figure with multiple angles, but we tend to think about it, or I think about it more as when I draw it, I'm making multiple line segments in order to create it. So a polygon is a multi-sided shape. And remember, it can only be made up of line segments, and they must all connect in one continuous chain back to where they started. So a couple of rules were we can't have any intersection, so we can't draw something like that, even though that's all, in theory, straight line segments. It's not a polygon because the line segments cross right here. It also has to close itself and can't have any curved parts. So we can't have something that's like a curve and then some straight pieces. That would not be a polygon because there's a curved side. And in theory, all these others were meant to be drawn with all straight sides. Okay, so the next thing we need to review is convex versus concave. So remember, convex means that all of the corners point outward. None of them point back into the shape. So a convex six-sided polygon would be a hexagon, and I could draw it something like that. So 1, 2, 3, 4, 5, 6. So not drawn terribly well, but you get the idea. That's kind of a hexagon. And it's convex because all the corners are pointing outward. And you could also think of that as all the interior angles are less than 180 degrees. Concave, on the other hand, means at least one of the corners is caved in, pointing into the shape. So concave six-sided could be something like 1, 2, 3, 4, 5, 6, like that. So here we have this corner points into the shape, and this interior angle right here is greater than 180 degrees, so that makes this whole shape concave. Even though only one corner is concave, that's enough that the entire shape is now concave. So there could be one or more concave angles within that shape. Regular, remember that means a combination of all the sides and all the angles are the same, so equilateral and equiangular. So equilateral and equiangular. So we know that for triangles, that's an equilateral triangle, but remember that polygons of any size can be regular. So our regular four-sided shape is a square. It has 4 equal sides and 4 equal angles that are all 90. We can have a regular pentagon, hexagon, octagon, any of those shapes. So like a stop sign is a regular octagon. I'm sure I can't draw one very well right here, but not terrible. So 8 equal sides, 8 equal angles. So anything regular is always every side and every angle is equal. All right, the sum of the interior angles in a triangle, we know that from the triangle sum theorem, is 180 degrees. And that's going to be really important for understanding bigger polygons as well. So we're drawing a rectangle and labeling interior and exterior angles. So here's a rectangle. And our interior angles would be here. So these are interior. And then to form exterior angles, we extend the line segments, but at each corner, we kind of want to go around clockwise or counterclockwise to make all of the matching exterior angles. So for example, if I extend this side here to form this exterior angle, then I want to go around So I extended the left side. Now I want to go to the top side and extend it next, and then the right side, extend it, and then the bottom side and extend it. So I'm forming my exterior angles here, which I could have drawn in a different color. So my orange are my 4 exterior angles. So we could have gone the other way around, right? I could have extended the top side to the left, and then the left side down, the bottom side right, and the right side up. But what's important is I'm kind of following it around, clockwise or counterclockwise. I tend to prefer to go clockwise. I don't know, it's just my preference. The sum of the interior angles of a rectangle. So we know that these are all right angles, meaning they're all 90 degrees, and that means that the sum must be 360 degrees. So looking at these things, we want to fill in some vocabulary. So we know that a triangle has 3 sides and 3 angles. A quadrilateral has 4 sides and 4 angles. Pentagon, 5 sides, 5 angles. Hexagon is 6. Heptagon or septagon, so there's 2 names for that one, is 7. Octagon is 8. Nonagon is 9, and decagon is 10. And also recall that for bigger shapes, we can just call it an n-gon. So an n-gon has n sides and n angles. So we can use that to represent a 20-sided or 30 or 37-sided shape. Okay, draw the following shapes. A rectangle, we've already drawn up above, has 4 right angles. A parallelogram, well, technically the rectangle is a parallelogram, so I could just draw that again, but to differentiate it, let's draw a parallelogram that's not a rectangle. So this is a 4-sided shape that has 2 pairs of opposite parallel sides. So the key thing here is that's parallel to that, and that is parallel to that. So that's also true in a rectangle, but this one is a parallelogram, but not a rectangle. And then a trapezoid is a shape that has 1 pair of parallel opposite sides. We call those bases. So I could have this base and this base that are parallel, and then I could have these 2 sides which are not parallel. And those 2 sides could be equal or not equal. So just like isosceles triangles, we could have an isosceles trapezoid, or we could have a non-isosceles trapezoid like I drew here. So that's all hopefully review stuff. Apparently I missed a couple of things, so let's just go back and add those. Interior and exterior angles of a triangle. That would have made sense to do before the rectangle, but let's go ahead and do that here. So we're going to draw our triangle. We have our 3 interior angles here. And then just like we did for the rectangle, we want to extend our segments and then follow it around the shape. So I'm going to start with this one arbitrarily, and then extend this one, and then extend, I did it wrong, didn't I? I didn't follow the thing I said. Okay, so I extended the left side, now I go to the right side and extend it, then I go to the bottom side and extend it. So now if I follow around, my exterior angles should kind of follow clockwise around the shape and always be supplementary to the interior angles. Okay, so we filled that missing piece. Then we were missing kite and rhombus. So I'm not sure you actually know these shapes. I think you know a rhombus. A kite you probably are familiar with from like just actual kite shapes, which is we have 2 equal sides. So these 2 are equal. And then we have 2 other different equal sides. So here, unlike trapezoids, parallelograms, and rectangles, nothing is parallel, but we have these 2 sides, 2 short sides equal and 2 long sides equal. So you could think about then splitting that and making 2 isosceles triangles out of it. Then a rhombus is, I could draw a square is a rhombus, but a rhombus is a parallelogram that has 4 equal length sides. So we could draw it as a square with 4 equal lengths, but typically we're going to call that a square rather than a rhombus. So we would draw it as a parallelogram version where all 4 of these are equal in length I don't know if those actually are, but that would be a rhombus as long as all four of those sides are equal. So these things form a family of quadrilaterals, and we'll be talking a lot more about that in the coming few days. All right, so angles in a polygon. This is our new material for today that you may know or may not know. What did the little boy say when his parrot flew away? I think he said Polly's gone. That's a bad dad joke. Polygon, a plane figure formed by 3 or more, I guess, line segments? Seems like segments. Regular polygon, all angles and all angles are congruent and all sides are congruent. So equiangular and equilateral. Consecutive vertices may be a new vocabulary. So that means if we're following around the shape, clockwise or counterclockwise, the vertices we encounter back to back. So this one and this one would be consecutive. This second one and this third one would be consecutive. So basically, they are endpoints of the same side. Then a diagonal is a segment that connects two non-consecutive vertices. So basically, we draw all of the segments that connect the consecutive vertices, and that outlines the shape. But if we draw a segment between any two non-consecutive vertices, all of these lines are called diagonals. So we may be more familiar with, on a rectangle, there's only one way to draw a diagonal in each direction because there's only that many vertices. But when you have more vertices, there's lots of diagonals you can draw. So I can draw diagonals between every pair of non-consecutive vertices. So I don't think I caught all of them. So there's one here, and there's one here. Right, so there's lots of these things. Still, I'm not sure that's all of them, but close enough. So lots of ways to draw diagonals. And then the last thing, which we talked about on the last page, an n-gon, is a regular polygon with n sides or angles. It has n of both sides or angles. Okay, so now we want to do this activity here where we're going to draw all of the possible diagonals from one vertex. So basically, if I start from here, there's only one diagonal I can draw because these two vertices are consecutive with this one. So there's only one non-consecutive vertex, and I would draw that diagonal. Triangle, there's no way because all vertices are consecutive to each other. This one I drew a bunch of diagonals, but if we just pick one, let's just pick this one, and we're going to connect it, all of its diagonals. So we can't connect to these two because those are sides. So we can draw 1, 2, 3 diagonals. And then I want you to go ahead and draw the other 2 if you haven't already. So draw all of your diagonals and see what you end up with. All right, so notice that when we draw these diagonals, so I'm going to start from the vertex here, go here, and here. Whenever we draw these diagonals, no matter how poorly we draw them, we're ending up with triangles within our shape. So here I'm going to start from this one. We'll go 1, 2, 3, 4, 5, 6. So in a triangle, we have one triangle. In a rectangle or a quadrilateral, we have 2 triangles. So let's go to a pentagon next. With 5 sides, we have 1, 2, 3. Hexagon, 1, 2, 3, 4. And then octagon, 1, 2, 3, 4, 5, 6, 7, 8. Is that a nonagon? 1, 2. Let's look. 1, 2, 3, 4, 5, 6, 7. Yeah, it was a nonagon. Okay, so let's write our shape names. So we have a triangle, we have a quadrilateral, we have a pentagon, we have a hexagon, and we have a nonagon. So the number of sides we knew from the previous slide is going to be 3, 4, 5, 6, and 9. But the number of triangles follows kind of a pattern as well. A triangle has one triangle. Our quadrilateral had 2. our pentagon had 3, hexagon had 4, and nonagon had 7 triangles that we can draw by making all those diagonals. And that should make a lot of sense, because if you think about the number of vertices, or the number of sides, when we connect this vertex to all the others, we're skipping 2 of them, right? We're skipping the 2 consecutive vertices and connecting to all of the other ones. So we end up with 2 fewer triangles than we have sides. So triangle is always 2 less than sides. So number of sides minus 2 equals number of triangles. Now, since we have these triangles, I know that each triangle has 180 degrees. So this triangle is 180. And as we saw on the first page, a rectangle has 4 90s, which we knew is 360. But now we're looking at that slightly differently. We're seeing this triangle has 180 degrees, and this triangle has 180 degrees. And if we add those 2 triangles together, we make all the corners of the shape. So part of it lies in this triangle and part lies here for this corner of the rectangle. But that doesn't matter. If we add them all together, we're going to come up with 360 degrees. Similarly here, we have 1, 2, 3 180s, so we end up with 540 degrees total. Here we have 4, so that would be 720 degrees. 400 plus 320, yeah, 720. And then here we have 7 triangles, so that would be 700 plus 560 is 1260 degrees. I'm going to double check that I got that right. 180 times 7, 0, 6, 5, 12. Yes, good. I can do the math. So we're seeing a pattern here where the sum of the interior angles is always going to be 180 times 2 less than the number of sides, because it's 180 times the number of triangles that we can split the shape into. And these, importantly, are non-overlapping triangles, right? So that's why we're starting from one vertex and drawing all of its triangles. That way there's no way for them to overlap. Whereas when I drew that hexagon initially and connected a bunch of different diagonals, those triangles overlapped, so we wouldn't be uniquely counting all of the corner angles. Okay, so our polygon interior angle theorem says the sum of the measures of the interior angles of a convex n-gon is. So we know that there's going to be an n minus 2 in there because that was our number of triangles. And then it was that times 180. So 180 times n minus 2 is our total interior angles, and it is important that this is a convex n-gon. Remember that with concave polygons, we end up with this big angle that's bigger than 180 degrees. So it's not going to follow this rule anymore. We would need to add some extra amount per concave angle. But for the theorem, we don't need to worry about that. If you want to challenge yourself, think about how would you generalize this for concave shapes. So how would you modify this? You would need to say it's going to be 180 times n minus 2 plus something in order to account for the concave angles. And so you could call the number of concave angles C and say, how would you modify it to make it work for that? So a corollary for this theorem, remember corollaries are things that kind of just come along with the theorem for free because they're using the same information to generate them. So the measure of each interior angle of a regular n-gon is going to be, we know the total is 180 times n minus 2. And then if we want to know each one for a regular shape, we know that each one, so if I draw a pentagon badly, say this is regular, it's very much not. If we know all 5 angles are congruent, and there are n angles, which is 5, then I would just divide the total into those 5 equal pieces. So for an n-gon, we would divide it into n equal pieces. So if I had a 12-sided shape, I would do 180 times 12 minus 2, so that's 1800, divided by 12, so that each of those 12 angles gets an equal share. And the most common mistake that I see made here is when you plug in n here, we take away 2, but here we're not taking away 2. We're using the total number of angles. So don't divide, if you're, again, plugging in 12, we do 180 times 10, but don't divide by 10, divide by 12. And you can notice that mistake easily if when you divide it, you end up with 180 again, right? Because if we multiply 180 times 10 and then divide by 10, you just get 180 back. And we know that our angles in a polygon can't be 180 because then they'd be a straight line. They wouldn't make a corner. So they have to be something less than 180. Okay, find the sum of the interior measures of a convex heptagon. So hep means 7. Remember, we can use heptagon or septagon for that one. Either one is acceptable. And if we have 7 sides, we need to do 180 times 7 minus 2. So that's 180 times 5. That's 500 plus 400, so that would be 900 degrees. Find the measure of angle A. Okay, so angle A is here. And when we're doing this, we have 1, 2, 3, 4, 5. So we know our total is 180 times 5 minus 2. So we end up with a total for a pentagon of 540 degrees. And you're welcome to memorize some of these common numbers instead of multiplying them out every time. That's totally up to you. So like we know a triangle is 180, we know quadrilaterals are 360. If you want to memorize pentagons are 540, hexagons are 720, and so on, feel free to do so. It's not a problem. You can also memorize the individual angles of the regular shapes if you are into memorizing stuff. I would rather just multiply it out every time because I don't like memorizing. Okay, so rewriting this a little bigger, we have 87 degrees here, we have 112 degrees here, and we have 91 degrees down here. Now, the trick with this one, this is a really good example because we want to make sure that we always add up the right number of angles to make this number. And we need 5 angles to make 540. So we do 87 plus 112 plus 91 plus angle A. But notice that only gives us 4 pieces. So before we start adding these, it's really important that we check every corner of the shape and make sure it's labeled. So since this is shown as equal to this, we're going to put another A over here. So we're going to add another A, and we end up with 5 numbers that we're adding together. So that's 199. Borrow 1, we get 200 plus 90, so that's 290 plus 2A equals 540. Take away 290, we end up with 250. So then divide by 2, we get A equals 125 degrees. Okay, so that's a really common trick that you'll see on polygon problems, is either having an unlabeled corner or maybe a corner that's marked with a right angle, like as a 90-degree corner, and then hoping that you'll forget to add in the 90 for that. So little tricks like that are really common in this section, so watch out for those. Okay, polygon exterior angles. This is one of the neatest things to me in geometry. I love this thing. So the sum of the measures of the exterior angles from each vertex of a convex polygon is simply 360 degrees, which sounds crazy that no matter what shape you make, no matter what polygon, the exterior angles always add up to exactly 360 as long as it's a convex shape. And this is not only for regular ones, this is for every one. Any pentagon, any hexagon that you draw is going to have exterior angles that add up to 360. So the measure of each exterior angle of a regular polygon, so we're taking our total of 360 and dividing it by the number of angles, because the number of exterior angles is equal to the number of interior angles. So just 360 degrees over n. So before we do these 2 examples, I want to show you one of my favoriteest videos. So this is a visual demo. We have a triangle, we have a quadrilateral, we have a pentagon, in a hexagon. Each of them has their exterior angles drawn. These are all going counterclockwise, I believe. I said I like to go clockwise, but it doesn't matter. As long as we go around the shape in one direction, that's what matters. So these are all the exterior angles, and look what happens if we collapse these shapes. If we bring them down and reduce the area basically to 0, all of the exterior angles come together and they all form circles. And we know that a circle has 360 degrees. So that's a really, just to me, very cool visual demo of how those exterior angles always add up to 360, no matter what. We can have big angles, small angles, but together they all come down and collapse to make that 360 degrees when you bring them together down to a single point. So I think that is really cool. All right, so let's finish out this page. It says the measure, we did the corollary. Find the measure of each interior angle and each exterior angle of a regular dodecagon. So that one wasn't in our list. Dodecagon, we knew decagon means 10 and do means 2. So ones a little bigger than we went were undecagon, which is 11, and dodecagon, which is 12 sides. So probably should know up to 12 is normally where we stop. So interior angles, and it's regular, meaning we know they're all the same. So the interior are 180 times, oh, this is the one I used as an example, 12 minus 2, and then we'll divide by the full 12. So we get 1800 over 12. Both of those are divisible by 6 pretty easily, so that's 300 over 2, which is 150 degrees. So each of them would be 150, and there's 12 of them total. So if you remember when we first looked at regular polygons, we saw that the more sides you add, so if you have a whole bunch of sides, we start ending up with a shape with all these teeny little sides that becomes more and more like a circle. So each of those angles is getting bigger and bigger and smoothing out to where the lines are almost just going one straight into the next with a full 180 degrees between them. Now it can never reach 180 degrees because that would not be a polygon anymore, but the more sides we add, the closer this gets to 180. All right, exterior angles. We know that there's 360 total, and we're dividing by a total of 12 sides. So each one must have 30 degrees. And that's a really nice double check because an interior angle and an exterior angle have to be supplementary. So 150 and 30 are supplementary, so excellent. That gives us 180 total. All right, the measure of each interior angle of a regular polygon is 168 degrees. So before we try to solve for how many sides it has, let's use some deductive reasoning. We know that this number is bigger than that one, and we know that adding more sides makes bigger angles. So we can start off immediately and say that this n-gon is more than 12 sides. How many more we need to solve for? So we're going to set up 180 times n minus 2 divided by n equals 168 degrees. And then I would just go about solving that like normally, so I would distribute and multiply that over, so 180 n minus 360 equals 168n. Move everything around, we would get 12n equals 360, so n equals 30 sides. So yes, it's definitely more than 12 and significantly more, right? Because we're a lot closer to our total of 180 than we were here, or to our theoretical maximum of 180. All right, so the rest of today is some practice. I think there was enough practice in the notes that I'll just let you work on those on your own. But there will also be an answer key if you need to review what you've done on it.